Okay, welcome back, everybody. Did I get a chance to see your email? No, but I can look right after class and get back with you. Okay, so at the end of I guess Wednesday's lecture, we had done uh, this application of partial derivatives where we had written out the equation for the tangent plane to the graph of a function. So we used the fact that the graph of a function of two variables was actually a special case of a level surface for a function of three variables, and we had this fact that if we computed the gradient vector for a function of three variables, that vector was the normal vector to the tangent plane of the level surface associated to some level for that function of three variables. All right, and then of course we use this tangent plane to approximate, right, to give a tangent plane approximation to a function in the same way that we did in Calc 1. So again, as I always say, I'm going to be beating you over the head with this interpretation of all of this or rather the interpretation of all the Calc 1 stuff into what we're doing now for functions of more than one variable. And so the thing that we're interested in today is to mimic what we did in Calc 1 concerning the analysis of functions, which was to discuss their extreme values. So in fact, this was basically the main application of derivatives in Calc 1, right? So when you move on, right? So you might say, like, what comes after Calc 3 if you're wanting to go and study math? What comes next after Calc 3? Right? There's Calc 1, 2, and 3. What is Calc 4? Well, there is no Calc 4. That's not what it's called. After Calc 3, it's called Advanced Calculus, okay, which can be thought of as Calc 4. But really what you're doing in that class is you're going back to Calc 1 and you're proving everything, and you're being a lot more rigorous. And so the field or the subfield of math that calculus leads into is called analysis. Okay, and so if you see anyone saying that their field in math is real analysis or complex analysis, analysis is the word that calculus becomes. Okay, so calculus leads into what's called analysis. And so you might say that Calc 1 is like analysis for functions of a single variable. Calc 3 is analysis for functions of more than one variable, and so on. And so the reason it's called that, of course, is that the idea is you were analyzing real valued functions of a single variable in Calc 1, and what is kind of the thing that culminated in? The idea was that if I gave you some closed form expression for a function, so say I gave you some function as, I don't know, right, like x cubed plus 2x minus 5 over x minus 1, x plus 7, right? So maybe in Calc 1 land, I give you this function, right? So closed form expression for a function like this. What was the thing that you were told to do, right? What was kind of like, this is the last thing you're doing before you talked about integration. Well, the thing that you would have been expected to do is to sketch the graph of this by hand, right? And that graph would need to include some important points. So where this thing intersects the y-axis, where it intersects the x-axis, if it does, where it has horizontal and vertical asymptotes, if it has any. So a horizontal asymptote is a limit at infinity. Vertical asymptotes are where the function limits to infinity at some, finite x. So vertical, horizontal asymptotes, y-intercept, x-intercept, and then other points of interest would be places where this thing had relative mins and relative maxes, right? That was what was important. Maybe, depending on the function itself, you'd be asked whether the function had an absolute or global max or min, right? And so it turned out, right, that a lot of that stuff you could have actually done with like pre-calc level knowledge, right? So things like x and y intercept and horizontal and vertical asymptotes, you could basically do that with pre-calc stuff. Okay, so really, what was it that you actually needed Calc 1 for? Well, what you needed Calc 1 for was being able to find those relative mins and relative maxes. And that was why you needed Calc 1, and because you needed the derivative in order to do that. In fact, it's impossible to find those things without the derivative. Okay? And so it turned out, right, that those were actually the important things. And talking about global extreme values or absolute extreme values, there could be interesting questions asked, but those were somehow less important than the relative extreme values. So how was that? Now, I'm not claiming that what I draw here is the graph of this thing. So, here, I'll get rid of that. Okay, let's say that in Calc 1, I'm considering a function, and here's the function that I'm considering. Okay, so my function does this. Okay, there's my function. All right. Now, just to refresh your memory on some of the terminology here, well, what would you call this? Right? This point would be the relative max value for my function f. So if this is my function f of x, this would be called the relative max value, and we might say that the relative max occurs at some, say, x naught, right? Okay, so relative max happens at x naught. The relative max value is f of x naught, right? It's f of x naught. Okay. What is the idea behind a relative max? The idea behind a relative max is that in some window about this point x naught, right, if I look closely enough, right, then at this value, my function is higher than at any other point in this window, right? Now, another way to say this, instead of relative max value, we might say a local max, okay? And the reason why local can sometimes be a nicer word to use there is because as I zoom out, right, as I make this window bigger and bigger and bigger, this is no longer going to be a maximum, right? Because if I make the window big enough, then I'm eventually going to be including, say, a point like that, which is clearly larger, right? It's clearly higher, okay, than this value. And so it's not an absolute max or a global max, it's a relative max or a local max. Okay. In fact, let's say that I give myself a window here. So I give myself a window. We'll call this window AB. So there's my closed interval. And it's clear that these points that I've identified on the graph, so this would be f of b, and this would be f of a. These points, so f of b, right, so on this interval, f of b is higher than any other point, right, that the graph of the function attains in this interval. And so here would be the global max, right? This is the global max, or sometimes you'll hear the word absolute max, right, would happen here, right? And here would be the global min. This point, of course, would be an example of a relative min. Okay. Now, I'll ask chat here. I'll ask chat here in a second, so let me say something first. The global max and the global min, put more simply, this is the largest value of f on the domain in question. So if the domain in question for this function f is the closed interval ab, then the largest value it attains is here. This is its global max, f of b. The smallest value it attains is f of a. Now, you might think that those are the two most important values when you're talking about mins and maxes, but they're not. Okay, and the way to see that they're not is look at this function that I've drawn here, right? So the function I've drawn here looks like it's doing something like this. The idea is this function, right? Maybe this function is defined on all the reals, but the domain in question that I'm concerned with at the moment is just this closed interval AB. Okay, and so if I ask you where's the global min, where's the global max, you're going to point to these 2 points, the endpoints, right? That's where it happens for this function. Doesn't have to be that way, but for this function, it happens at the endpoints. Okay. But what if after I've asked you that, I then change my window a little bit, right? So instead of having the closed interval AB, I have the closed interval CD. Okay. And then I ask you again, what's the global min? What's the global max? Well, what happens, right? Those values change. Now my global min is this point, right? It's this value. And my global max is this value, right? And as I expand that window, the values that make up my global min and global max change. Okay, so global mins and global maxes they could change if you expand or shrink the window, right? If I shrink my window enough, then the global max and global min would actually be these relative maxes and the relative min, right? In fact, that's kind of a definition of them, is that if I shrink my domain enough, right, if I look close enough, then this is definitely the max, and if I look close enough here, this would definitely be the min. So what am I trying to say? The global maxes and global mins for a function can change if I alter the domain in question. But notice that the relative maxes and relative mins don't. So if I ask that question, on the first interval, AB, what are the relative maxes and relative mins? Well, there's one and there's one, right? There's relative max, there's relative min. Those are the relative extreme values for this function in that interval. Okay, and then if I expand my interval to be the interval from C to D, and I ask you what are the relative extreme values in that interval, it's the same, right? I didn't get any new ones. It's possible that I could get new ones added in here, but I didn't get any new ones. I'd still just have these, right? So it didn't change. So what is it that I'm trying to say here about relative extreme values? In a way, they're a lot more important than the global extreme values, okay? Because the global extreme values could just be an artifact of whatever window you're looking in, right? Whereas the relative extreme values are things that are like inherent to the function itself. A better way of thinking about it is the relative extreme values tell you the shape of the function, okay? And so the function itself, right, once you know its relative extreme values, you know something about the shape, whereas the global mins and maxes may really just be telling you something about the size of your interval, right? Okay, so that's the thing. The relative extreme values are more important. They tell you the shape, okay? So relative extrema tell you the shape of the function. Okay, so this is kind of a refresher course on how this worked in Calc 1. All right, now, how did I find the relative mins and maxes? So this is the question I'm asking for chat. How did I find the relative maxes and relative mins? How did I find these points? Okay. The other things I claim I could find without calculus, so kind of spilling the beans here. How did I find relative maxes and relative mins for a function? Okay, so someone said set the derivative equal to 0. What am I doing when I do that? If I set the derivative equal to 0, what am I doing? So here, you might look at this and say, well, setting the derivative equal to 0 is saying that you're looking for places where the slope of the line tangent to the graph is horizontal, right? It has slope 0. Okay, and that definitely makes sense. That's good. And for this function, that is definitely what you would do, right? You would look for exactly those points. But what if I had a function that looked like this? So here's my function, f of x. I still want to say that this is a relative min. Okay? But there's a problem here. Right? What's the problem here? Well, the problem here is that the derivative's not 0 here, right? In fact, the derivative doesn't exist here, right? Because here the derivative is some negative constant, here it's some positive constant, and so that derivative doesn't exist there. It's not differentiable there, okay? But this is also going to be okay. And so, what did we call points where the derivative was either 0 or non-existent? Right? What did we call those? Anyone remember the word? So we took the derivative and looked for where it was 0 or undefined, right? This is generally our process. Critical points, exactly. So this led to critical points. In fact, that was our definition of what a critical point was. What was the reason we did this? We had this big fact, right? So here was our big fact in Calc 1. That was the reason that we did this. So relative extrema, that is mins or maxes, could only occur at critical points. All right. That was our big fact that we used over and over and over again in Calc 1. Okay. Now, of course, be very careful to not confuse this statement with its converse statement. Right? So, this statement is the statement relative extrema happens at x naught implies x naught is a critical point. That is what this statement is. What this statement is not, so this is not the statement x naught is a critical point, implies relative extrema happens at x naught. Okay, this statement is true. This converse statement is false, right? So this is false. Why is it false? Can anyone give me an example of a function that has a critical point but doesn't have a relative extrema, or doesn't have a, relative min or max at that critical point? There was a nice canonical example. It was like the first example you were taught. Yes, x cubed, exactly. X cubed at x equals 0. That's a quick example that shows you what's happening here. Here's x cubed. Okay, so here's the graph of x cubed. At x equals 0, what happens? If you take the derivative of this thing, of course, you get 3x squared. If you plug in x equals 0 here, you get 0, so it's a critical point. 0 is a critical point, but what happens? The tangent line, of course, does go horizontal, but it doesn't change sign. So as someone else noted in the chat, what was important here was that the derivative changed sign. So what did you have to do, right? It would have been really, really simple for us if this statement was true, because if this statement was true, since what we're interested in is finding relative extrema, we would just find the critical points, and then we would have automatically found the relative extrema, right? Okay, so this isn't true. So we can find critical points, which is the only points where relative extrema can happen, but then we have to test them. So in Calc 1, there were two tests that we came up with. There was the first derivative test and the second derivative test. Okay, so the first derivative test was something you could always do, but it was a little bit cumbersome, right? It was cumbersome because you had to actually not just compute the derivative and find the critical points. You had to test values on either side of the critical points, and it could be really annoying. And so the second derivative test was really, really nice in the fact that with the second derivative test, you didn't have to test any values. All you had to do was just plug a number into the second derivative. Okay, so the second derivative test was a lot easier to do than the first derivative test, but there was one problem with it, which is that it could be non-determinate. Right? The second derivative test had this one fatal flaw that for some functions and at some critical points, it could be non-determinate. If you plugged that critical point into the second derivative, and you got 0, you couldn't say anything, right? That was an issue. Okay, now the reason I go over all of this is because what we do in Calc 3 is going to be almost exactly the same. It's going to follow that exact same process. So what is the idea in Calc 3? How do I move that to Calc 3? Okay, well, the idea is that I have a graph, and maybe my graph, maybe part of my graph looks like this, right? And maybe it dips a little bit, but I'm going to actually separate these so that it looks nice. So we have some graphs, and maybe at this part of the graph it looks like a hill, but maybe over here there's a part of the graph that looks kind of like a bowl, right? And maybe it kind of looks like a bowl over here. So there it looks like a hill, there it looks like a bowl. Okay, so the idea is that I have some region down below. So this region I'll call R. So this is my domain. And as I've said, you can think about this as like the shadow cast by the surface or the graph of the function in question. If you're shining a light on it from the positive z direction, right? This R, this region that the function's defined on, is your domain, or it's the shadow cast in that way. Okay, so if I'm thinking of it like that, the idea is that above this R is the graph of my function. Maybe it has some places where it's got some hills, maybe it's got some bowls. I want to know where these are, and I want to know, if I know all those points, can I kind of sort of reconstruct what the graph of the function looks like? That's the hope here. Okay, and so this is what a relative max looks like in Calc 3, right? So here's a relative max. So that relative max value would occur at the point, say, x naught, y naught. And this point here would be an example of a relative min. And that would occur, at some other point here, x1, y1, whatever. Okay. So we have relative maxes and relative mins. Okay. Now it turns out this isn't going to be a complete picture. We're going to get something that we couldn't really get before. Okay, we kind of, sort of have a hint of this from that example I just did, x cubed, in Calc 1. But we really, really get something that couldn't happen in Calc 1 and Calc 2 that is going to happen for us now because we have an extra dimension here. We also have something very annoying that we'll talk about when we talk about global maxes and mins that makes the whole question a lot harder than it would otherwise be. So this is what relative maxes and mins look like, but how do I find these? So how do I find them? How do I find where those happen? Well, it's exactly the same process as Calc 1. So the idea here is I find critical points. So definition. I will say that a critical point for a function f of x, let me call it f of xy. That's not an x naught here. So a critical point for a function f of xy is a point x naught y naught in R, that is the domain of f, for which the gradient of f at x naught y naught is equal to the 0 vector, or is undefined. Now, this is exactly like our definition for Calc 1, except our gradient now replaces the role of the first derivative. Of course, what does this condition mean? If the gradient is equal to the 0 vector, it means both components are 0, but the components of the gradient are the x and y partials. So really what this means if I translate this over here, what this means is that the x partial of f at x naught, y naught is 0, and the y partial of f at x naught, y naught is 0. What would it mean for the gradient to be undefined? It means that one of the components is undefined. So it doesn't have to be undefined in both slots. So maybe it has an x partial at that point, but not a y partial, or vice versa. But one of them would be undefined. And so these are critical points. Now, why are we finding the critical points? Because we have actually the same fact that we had in Calc 1. So fact, a relative, and it's important that the word relative is included here. So a relative min or max can only happen at a critical point. Okay, but as we'll see, this need not be, the converse need not be true. In fact, the converse is false, meaning that, when I find all these critical points, the way to think about this is these are candidates, right, for where relative mins or maxes can happen, but they very well may not happen there. As we saw, this wasn't even true in Calc 1, where we had less going on. It also wasn't true, but it's not true for us here either. So a relative min or max can only happen at a critical point, but just because you have a critical point doesn't mean that a relative min or max happens. Nothing could happen there. Okay. All right. And so let's do an example here. Let me pick one. There was a good one I saw in the textbook earlier. Yeah, here's a good one. So let's let f of xy be the function 3 minus x squared plus 2x minus y squared minus 4y. Okay, and let's find all critical points of f. Okay, so looking ahead here, we can clearly tell the gradient's not going to be undefined anywhere because this is a polynomial in x and y, so it's going to have all of its partials. We don't have to worry about that. And again, as I said, right, true to my word, to solve every question in this section, in chapter 13, I take partial derivatives. Okay, so I got to be comfortable with that. So I take the x partial here. The x partial of f, let's just go through here. X partial of 3 is 0. X partial of minus x squared is minus 2x. X partial of 2x is 2. X partial of the rest of these terms just involve y, so it's 0. So my x partial is minus 2x plus 2. My y partial is y partial of 3 is 0. Y partial of minus x squared is 0. Y partial of 2x is 0. Y partial of minus y squared is minus 2y. And y partial of minus 4y is minus 4. Okay. All right. And so now I want to set these equal to 0. Okay, so I set them equal to 0. When I set them equal to 0, I get two equations. Now, this is a very simple example, and so each equation only depends on one variable. That's not going to be the case in general. In general, you're going to have two equations in x and y, right? Now, there is not a general process for doing this because I'm not guaranteeing that you're always going to have linear equations, right? If these were linear equations, then there's a nice generic process you could always use. But you could have two nonlinear equations in x and y, and so maybe you have to do some algebraic trickery to solve them here, okay? And I'll do some examples of that later. But here, of course, you get two equations. These have to be true simultaneously. Okay, again, not going to be a problem because each one only depends on one variable here. So from the first one, I get x is 1, right? So the first one implies x has to be 1, and the second one implies that y has to be minus 2. Right? And so 1 minus 2 is the only critical point of f. All right, now that's nice, but I want to know, how can I proceed from here? I found the critical point, but how would I be able to tell what's actually going on here? Well, this function is really, really simple. And so if I wanted to, I could look at this function and rewrite it a little bit. Let's rewrite f a little bit. So f of xy is 3 minus x squared plus 2x. But you know what? I want to make this nicer. I want to make this nicer. So if I wanted to make this nicer, what would have to come here for me to be able to factor this in a nice way? What would I need here? Well, if I put a minus 1 here, I'm going to be able to factor that as minus something squared. That'd be nice. Okay. Continuing on, I have minus y squared minus 4y. What would I need to write here to be able to write this as minus something factored? That's nice. Well, if I put minus 4 here, then that works out okay. But I'm just changing stuff, right? I'm not really allowed to do that. Unless, of course, I compensate by changing it back. Right, so I put a minus 1 here that wasn't there, so I can add 1. I put a minus 4 here that wasn't there, so I can add 4. Okay, so I can factor here. This is actually 3 plus 1 plus 4. That's 3 plus 5, so that's 8. So this is 8 minus x minus 1 squared minus y plus 2 squared, right? So f actually has a really simple form, and from this I can tell, oh wait, here I have this function, whatever it is, it's 8 minus something squared, so the smallest this can be ever is 0, otherwise it's positive because I'm squaring it, minus something else squared, smallest this can be is whenever it's 0. Okay. So what's the largest that this thing can be? Well, the largest this thing could be is when both of these quantities are equal to 0 simultaneously. When does that happen? Oh, right, at 1 minus 2. So from this, I can actually tell that 1 minus 2 is a relative max for f and a global max for f on the entire plane. Okay. Now, you look at that and you say, surely I'm not going to have to do this for every function I come across. No, that's one thing. And you couldn't do it even if you wanted to for most of these functions. This function had a very particular form. And of course, we're not going to be able to do this every single time. And so there has to be some method for determining what's going on here. All right. And so what is that method? All right. So here is where the second partials test comes in. Okay, but before I talk about the second partials test, I want to give you an example of a thing that can happen in Calc 3 that could not happen. It's a thing that didn't exist in our other examples, or in Calc 1 and Calc 2. And so here's another example. So consider, I've already given you an example of this type of function. So consider the function f of xy is y squared minus x squared. Okay. Let's find critical points. Okay. So there's only going to be one, as we'll see. So quickly, the x partial of f at xy is minus 2x, and the y partial is 2y. So 0, 0 is the only critical point. Okay. All right. So 0, 0 is the only critical point here. Okay. Now, the question is, what happens there? right? What happens here? Does a relative max happen? No, right? Does a relative max happen? No. Does a relative min happen? The answer is also no. Something else happens that is a little weird, okay? And so what is this something else? I'm going to cheat and actually draw the graph of this, okay? So the graph of this is, it looks like this, and I've drawn this in this class before. So this does something like this, just to give you a little slice of it. Smooth that out there. Okay. So the graph of it looks like this. And 0, 0 is exactly right here. Okay. Now, we did an example of this already when we talked about graphing things with cross sections. Okay. Exactly. It looks like a saddle. And that's exactly how we're going to describe this point. Okay. And what was the idea? Okay. Why does this have a special name? Okay, so what we call this here is 0, 0 is a saddle point. And this is what we're going to call all points that act like this. Well, what does it mean to be a point that acts like this? Why does this get a special name? Right? The question is, are there other points that are critical points that aren't relative maxes and mins, but also aren't saddle points? The answer is yes. Okay, there are points that are critical points, and there's not a relative max there, there's not a relative min there, and there's not a saddle point there. Just nothing happens. Okay, so a saddle point is something different, okay, from relative max and min. But what is it that makes it different? A saddle point is a blend of relative max and relative min. How? The idea is, and again, we're going to go back to when we did this with cross sections. If I look at cross sections of this thing, that is, I view planes cutting this thing like this, what do I get? I get this parabola, right? Is my cross section here. And 0, 0 is the apex. It's at the bottom of this parabola. So in that direction, what is this point? Well, it's a relative min. So looking at it from this direction, it looks like a relative min happens here. But if I were to take this object and turn it on its side and look at cross sections cutting through like this, what is the cross section I get? As we saw when we first did this early chapter 13 stuff. I get a parabola that is downward opening, right? And this point, this same point that was at the bottom of this parabola, is now at the top of this other parabola. So what is a saddle point? It's a point that looks like a relative min happens there in one direction, but in the perpendicular direction, it looks like a relative max happens. Okay, so a saddle point is kind of like a relative max and relative min smushed together. Okay, and neither of those happen there, so a relative min doesn't happen, a relative max doesn't happen, but it's like if you look just in one direction, both of those things happen. Okay, and that's why saddle points are this weird extra thing. Note this could not have happened in Calc 1 because we didn't have enough dimensions, right? You got to have a two-dimensional object to talk about this. Okay. So this was something that couldn't occur in Calc 1. Okay. So those are the three building blocks for our functions. So the points that we're going to try to identify are all the critical points where something happens, and we define something as being relative max, that is the top of a hill, relative min, the bottom of a valley or the bottom of a bowl, and saddle points. So those are the 3 points that we are going to, when we talk about analyzing a function of 2 variables, what we really want is to find out where it has relative maxes, where it has relative mins, where it has saddle points, and the idea is that if we really wanted to, we could piece together what the function looked like from those. Okay. Now the question is, how do I actually figure out what is going on there, right? Like, how would I have known what was happening without this drawing? Well, this is where our analog for this is actually our analog for the second derivative test, okay, comes in. So this is called the second partials test. And this is going to be our way of figuring out what it is that happens. It's going to be our only way of doing this. Okay, it's called the second partials test. Now, what does the second partials test say? Okay, so I have to define this thing first. Okay, so first of all, the second partials test is a thing that you only apply at critical points. So before applying the second partials test, you have to have found all the critical points for the function in question. Okay, so assume f has a critical point at the point x naught, y naught. Okay, and that f has continuous second order partials. All of them, all second order partials are continuous at x naught, y naught. Okay. Actually, we need them not to just be continuous there. We need them to be continuous on like a tiny disk around x naught, y naught, but you don't have to worry about that too much. Define d at the point x naught, y naught. So you're only applying this at x naught, y naught. Define d of x naught, y naught to be, so that colon, remember, means that this is being defined to be this thing. So define this to be the double x partial of f at x naught, y naught times the double y partial of f at x naught, y naught minus the xy partial of f at x naught, y naught squared. This is called the discriminant. Okay. So this is called the discriminant of f at a point, right? Since it depends on f, then, this is the discriminant of f at x naught, y naught. Okay. So I define this thing. I compute this thing at any critical point that I care about. And then I have 3 cases, really 4 cases. Okay. So, first case. If d of x naught, y naught is positive and f sub xx at x naught, y naught is also positive, then f has a relative min at x naught, y naught. We'll talk about in a second how you can actually use, you can also use the double y partial here. And before you even say anything, you're going to say, what if the discriminant is positive and the double x partial is like 0 here, right, instead of being positive? And I'll talk about that in a second. Okay, it turns out that can't happen. Okay, another case, if the discriminant is positive at that point and the double x partial is negative, then f has a relative max at x naught, y naught. Okay. No, the entire boxed thing is called the discriminant. Okay. The third case. So let's think here, right? Just in terms of trichotomy. I have the case when the discriminant's positive, and the second x partial of f is positive. That gives me one case, relative min. I have the case when the discriminant's positive, and the second x partial is negative. That gives me another case, relative max. You might say, what about the case when the discriminant's positive and the double x partial is 0? It turns out that can't happen. And so this covers every possibility when the discriminant is positive. Okay. So then I have the case that the discriminant's negative. If the discriminant is negative, then I actually don't need to check anything else. Then x naught, y naught is a saddle point of f. Okay. So the first two cover the case that when the discriminant's positive. The third one covers the case when the discriminant is negative. And so you might imagine there's another case here, which is if the discriminant is 0. If the discriminant is 0, I know nothing. Okay. If the discriminant is 0, you cannot say a single word about what happens at x naught, y naught from this test alone. Okay. So from this test alone, you can say absolutely nothing. You would have to be able to figure it out some other way. Okay. And this is the thing that should tell you, other than the fact that it involves second order partials, this is the thing that should remind you of the second derivative test in Calc 1. Right, so the second derivative test was a lot better than the first derivative test in the sense that it was more convenient. You just plugged in a single point. All right, you didn't have to test any intervals. You didn't have to draw, a line and test whether it's positive, negative, whether it switched, and what was going on there. You didn't have to do any of that. You just plugged in a single number. Okay, but the downside was that if it turned out that when you plugged it in you got 0, you couldn't say anything. Right, and so if the discriminant is 0, you don't know anything. In fact, I can show you examples of everything happening here. So relative max can happen when the discriminant is 0. Relative min could happen. Saddle point could happen. Or absolutely nothing could happen. Literally anything could happen in that case. So that's why you have to say that you know nothing there. This is the second partials test. Okay. So I don't have enough time to do an example here. So that's what I'll do at the beginning of class on Monday. But what I will do is the following, which is to say I'm going to at least give you the kind of the conceptual reason why this does what it does. Now you might look at this and say, what is this? Like, what is the discriminant? Where does this come from? Okay, this seems to be just totally random. Well, as we saw, right, I have function f of xy. And if I'm trying to think in the Calc 1 way, what is the closest I get to having the derivative of a function? Well, the derivative of my function is the gradient vector, right? So this is my first derivative, right? First derivative. Okay, and so my first derivative is a vector. My first derivative is the vector, it's got the x partial in the x slot and the y partial in the y slot, right? There's my gradient vector. What is the second derivative? Okay, so I started with my function, which is a real number, right? Or it's real valued, so it spits out real numbers. And then for the first derivative, I went from that real valued thing to a vector valued thing, so it's a vector of real values. For my second derivative, what is it that I'm doing here? Well, I would need to talk about a vector of vectors here. But what's a vector of vectors? It's just a matrix, right? A vector of vectors is just a matrix. So this second derivative would be a matrix. And it would be the matrix that I get by forming, so I would have the x partial of the x partial, right? So f sub xx would be in this upper left slot. And then here I would have the y partial of the x partial, so f sub xy, xy. And then in this slot, maybe I would have the x partial of the y partial, right? And then lastly, I would have the double y partial. This would be these are all of the second order partials, right? Yeah, you can think of it as kind of like the gradient of the gradient. That's kind of a way of thinking about it, yep. And so, this thing is called the Hessian matrix. So this is called the Hessian. Of F. Okay. Well, I have a matrix. Naturally, I am interested in when I have a matrix, I immediately have questions about it, many of which can be answered by a single computation. And the computation in question is taking the determinant. What is the determinant of the Hessian matrix of F? Well, it is f sub xx times f sub yy minus f sub yx times f sub xy. But what do we know about the mixed partials if f is nice? Well, if f is nice, these are the same. Right? So actually these are the same thing. So I can simplify this slightly. But what is that? Well, that's our discriminant, right? So the discriminant we're computing and testing the signs of, that's the determinant of the Hessian matrix. So the Hessian matrix is the second derivative of f, or at least as close as we can think about a function of two variables having a second derivative in this way. It's the second derivative object, right? And so this number we're computing, this, which is a real number, right? This is guaranteed to be a real number, is the determinant of that matrix evaluated at that point. And so the sign of the determinant breaks into all these cases, and those cases are the second partials test. Okay, so that is conceptually what's going on. All right. So on Monday, I'll do a bunch of examples, and then we will start into what do you do when you want to talk about global maxes and mins. Katya, yeah, you can assume that we're always going to be dealing with an f that is nice enough that the mixed partials commute like that. Yeah, so yeah, you don't have to worry about the exact assumptions. You can just always assume that that's the case. I'm not gonna trick you with anything or with any function where that's not the case. So yeah, on Monday I'll do a bunch of examples of these, and I'll show what happens when we try to move this over to the boundary. And we want to talk about absolute maxes and mins. So there's some real nasty stuff that happens there, but we'll take care of that. And then, like I said, afterward we'll go on to Lagrange multipliers, and your second exam will be after that. Okay, so anyway, I'll see you all on Monday.